So the next topic we need to cover is the concept of switching our variables to polar coordinates. Now, why would we want to do this? So we've talked about how if we have a surface, say some surface here, f of xy, over top of an area, some random area here, some region, we could find the volume in between. And the way we do that is we would grid off this region here. Each one of those squares would be the base of a rectangular prism. That rectangular prism would go up to the function. We'd find the volume of that prism, and then we would continue to do that over and over again. Now, the reason why we would want to switch to polar coordinates has to do with this region. So this region is in the xy plane. And let's say that region is a vertically simple picture. Okay, so something like this. And we want to define this region. Here's a function, here's a function, both functions of x. We would say that y is between g of x and f of x, and x is between, let's say, a and b. And we would do that, and that's what we did before. But let's just say this region doesn't look like that. Let's say that region looks more like, say, this, in that it's a quarter of a circle. So this is, say, x squared plus y squared equals 1, the unit 1 circle, and we're only looking at this 1/4 of that. And we go to grid it off. Well, we could still do that. We could still grid it off this way and grid it off this way. And we could say, all right, well, what's y between? Y would be between the x-axis and this curve. We could do that, over and over again. It's the same thing. I would just have to define this curve as a function of x, which would be y equals the square root of 1 minus x squared. And so that would be the top curve. The bottom curve would be 0, which is the x-axis. And then x would go between, say, 0 and 1, since this is a unit 1 circle. Okay? Doable, right? It's not that difficult. This upper limit of integration for my y is not going to be the nicest thing to work with. But let's just say, instead of gridding it that way, we instead gridded it this way. And like this. In which case, each one of these is not a square, but each one of these will be the base of a prism down here. So you think of this kind of being gridded like this, and then like that. And now this is the base of a prism here. We're going to call this a shape, which looks something like this. A polar sector, in which case that's the area of the base. We have to figure out what the area of one of those is. And then we would just figure out the height based off the function value, same as before. And then once we get the volume of one of those prisms, we add them all up and go from there. So it's just a different way of thinking about it. But why would we want to do that? Well, because the space fits into this type of grid much better than this type of grid. Okay. And so that's why we might want to switch to polar coordinates, because that's exactly the shape of polar coordinates. Polar coordinates isn't a rectangular system, it's a circular system. And so we would have to look at how do we do that. So the key to changing the coordinates is first to understand what the conversion formulas are, and we should know this by now. So we have our basic conversion formulas for rectangular to polar and vice versa. X equals r cosine theta, y equals r sine theta. Also, r squared equals x squared plus y squared, and theta equals the arctan of y over x. Okay, next what we want to do is we want to look at this polar sector. So again, this is sort of the picture I gave you before. So let's say we have this region that we're trying to divvy up and subdivide, but we're going to divide it in more of a polar fashion. So we're going to grid it off this way in more of this rotational aspect. We're going to look at one of these little polar sectors. Remember, this is going to be the area of the base of a prism, I should say. Okay, so you have this prism. This is your base. Then you're going to go up to the function with this base, and again, you're going to have another one of those right up here. And you got to figure out the volume of what one of these prisms would look like. Well, it's just area of the base times the height. But the height we know is the function value. So it's really just the area of the base. So we need to look at the area of one of these polar sectors. So there's a couple of measurements we're going to need. One is this distance this way, okay? And the other is this distance this way. Well, this distance this way is based off of two radii. So you have the radius from the origin outward to the outer edge, and then you have the radius from the origin to the inner edge. And if you look at that big radius and the smaller radius, we'll call R1, R2. If we take the difference of those two radii, that'll give us this distance here. And then we have two rotations. We have a rotation to here, and we have a rotation to here. And the difference between those two thetas, we'll call them theta 1 and theta 2, the difference between these would give us the distance here. So the amount of rotation versus the distance this way. So we have delta R and we have delta theta. Delta R is this distance, delta theta is this distance here. And so once we have those two measurements, we have almost everything we need for the area of this polar sector. I mean, if you thought of this as a rectangle, you would just need length and width, and kind of think of delta R and delta theta as that, but these are curved, so that's not quite right. So there's one more measurement we need, and the measurement we need is the distance to the middle of the polar sector, which we're just going to call R itself. Okay, so the distance to the middle of that polar sector. Remember, these polar sectors are arbitrarily small, so the middle of every polar sector could be basically at every single point in this string of radii. So if we look at that and we take those three measurements and multiply them together, R times delta theta, that will give me the area of one of those polar sectors, the area of the base of the rectangular prism. Not really rectangular prism, polar sector prism, I should say. The base is a polar sector. So if that's the area of the base, okay, there, that's the area of the base. If I then multiply it by the function value, but where x and y are now changed over to polar coordinates using r cosine theta and r sine theta, we should then get the volume of one of those prisms using that formula. So then what do? Once we have the volume of one of those prisms, we have to add all those up. Okay, we add all those prisms up. That should be a summation. Let's make that better. We add all those prisms up, and then we take the limit as the number of subdivisions goes to infinity, and that should give us the volume we're looking for. But that's exactly what double integrals do. So in this case, the double integral over the region in now polar coordinates, where we have the height times the area of the base, but the area of the base is based off of r delta theta, will give us this integral. The one thing that's you need to understand here is that how the area of the base turns into the differential component of this, plus an extra function. When we have a delta x and a delta y, when we integrate, that turns into dx and dy. Okay? The change in x, change in y, interval on the x-axis, interval on the y-axis. Okay? Dx, dy. So here, if we have r delta theta, the delta r and the delta theta should be dr and d theta, but we have this extra r. So there's this extra function here in the differential that comes into play when we switch to polar coordinates. So that's something that you need to be aware of. So again, look at this differential. It's not just, oh, dx, dx and dy is going to convert over to dr and d theta. It doesn't work that easily. Dx and dy converts over to r dr d theta. And it's very much like what we did back when we did substitution. When we had substitution and we said u equaled, I don't know, say 3x and du equaled 3dx, okay? du didn't just get to become a dx. You didn't just switch one variable out for another with an equal du and dx all the time. There's always was this extra function that tended to be there that made the substitution really fit the integral. Well, the same thing goes here. The dx and dy doesn't just switch to a dr d theta. What we're really essentially doing here by switching the polar coordinates is doing a substitution, just a very, very specific substitution here. And then the dx and dy essentially now is a dr d theta. All right, let's do an example. So here, let's let R be the region that lies between the two circles, x squared plus y squared equals 1 and x squared plus y squared equals 5. That's the region we want to integrate over. And we want to evaluate this integral over that region. So let's look at the region real quick. We have two circles, unit 1 circle and a unit square root of 5 circle, or radius, I should say, square root of 5 circles. So square root of 5 and 1. And you know that because this is r squared in each of the case. This is x squared plus y squared equals r squared. So you have these two circles, we want the space in between. So this is the space in between. That's the region we're integrating over. And we have this function, this random function, x and y, it's a surface. That function is going to be integrated over this area. So if we wanted to stay in terms of x and y, we would have to figure out what x is between and what y is between. So let's just think about vertically first, y. Y goes from here to here. Okay? But when I go over here, y goes from here to here, but also here to here. And when I get over here, y goes from here to here. And so the idea is I would have to divvy this up into a bunch of different regions. I'd have to basically cut it here, and I'd have to cut it here. And if I'm going to define what y is between, I would have to look at this region in here and say, well, y is between this half of the circle and this half of the circle. Then when I get to here, I would have to look at this space and this space, oops, and delete everything, this space and this space, and say, okay, well, y is here to here. That's a totally separate region where the upper one is still this circle continued, but the lower bound is different. And then I would have this one over here where I have the top half of the circle and the bottom half of the circle, same as over here, but different x values that I'm working with. And then here and here would be another region. So I would have to do this because the y interval and the x intervals would be changing in each one of these spaces. So if I wanted to do this, I would essentially have to do 4 different double integrals all added together, where this would be region 1, and the integral would be integrated over that piece. This would be region 2, this would be region 3, this would be region 4, and I would have to do each one individually, then add all those pieces together. Not ideal, so let's get rid of that. If I did this in polar, right? If I did this in polar, and I said, is there a way that I can define this like donut shape in polar in terms of r and theta? Remember, this is a radius 1, this is a radius square root of 5 circle. So r is the distance from here outward, right? So what I need to know is what this distance is. Here, 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 all the way around. Well, because these are two circles, that distance is the same all the way around. And what is r? Well, r is between 1 and square root of 5 the whole time. Now, once I have that radius, what I need to do is I need to fill in the donut all the way around. Well, that's the amount of rotation that radius would have to take. That's my theta. In this case, theta would go between 0 and 2 pi. So I can define this region really easily with r's and thetas all at once. Whereas if I had to do x's and y's, I would have to do it in 4 separate chunks. So this is why polar coordinates work so well here. All right. So now we know what our limits of integration are going to be. We know that dx and dy is going to convert over to r dr d theta. And all we need to do is convert x squared plus y over to polar coordinates, and we have everything we need to convert this integral to a polar integral. Well, what do we know? We know that x equals r cosine theta, so that should be squared, and y is r sine theta. So we end up with r squared cosine squared theta plus r sine theta. So this integral of x squared plus y dA should turn into the double integral of r squared cosine squared theta plus r sine theta. That's the function now. Times the differential dA is r dr d theta. And then order, well, looking at this here, constant, 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 order actually doesn't matter at all. So I already have dr and d theta, so let's just keep it that way. So r was 1 to square root of 5, and theta was 0 to 2 pi. And so this whole integral is now converted into polar coordinates, which is actually a lot easier than if we left it in rectangular coordinates. This is why we might want to switch to polar coordinates. Okay. So next up, do the integration. Well, don't forget you have this extra r out here, so that would have to be distributed in first. Okay. So we have 0 to 2 pi, 0 to square root of 5, r cubed cosine squared theta plus r squared sine theta dr d theta. Integrate with respect to r. Cosine and sine of theta are constant multiples, so 0 to 2 pi will sit. We would get r to the 4th over 4 cosine squared theta plus r to the 3rd over 3 sine theta between 1, this is 1 and square root of 5. Still have a d theta. So then I would get 0 to 2 pi times, put square root of 5 in to the 4th is going to be, what, 25 over 4 cosine squared theta plus square root of 5 in here would give me what? Square root of 5 would be 5 square root of 5 over 3 sine theta minus 1/4 cosine squared theta minus 1/3 sine theta d theta. So now we have to just do that integral. And once we finish that set of integrals, we're done. You may say, well, that doesn't look that easy. Well, it's actually not too bad. So let's look at that. So if we bring our integral together, we have 0 to 2 pi. I'll bring the cosines together. It's going to turn out to be 6 cosine squared theta. And I bring the sines together. It'll be 5 root 5 minus 1 over 3 sine theta d theta. So it's a single variable integral, so it should be no big deal. Cosine squared, we should have learned this back in Calc 2. We're going to need power reducing identity. 1 plus cosine 2 theta over 2. To be able to integrate that, I'll split it apart into two separate integrals. So let's say 0 to 2 pi, I have 6 times 1/2 plus cosine 2 theta. And then this is just sine theta, so that's not going to be a big deal. So 5 root 5 minus 1 over 3 sine theta. And then that whole thing, d theta. So now we're ready to go. So 6 is a constant multiple. Integral of 1/2 would be 1/2 theta. Integral of cosine 2 theta would be plus sine 2 theta over 2. And then this one will be plus 5 root 5 minus 1 over 3 times sine, which would be negative cosine. So let's change this to a negative. And then we evaluate that between 0 and 2 pi. So then I plug in the 2 pi here, 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 and then the 0, and we're done. So what do we get? Let's put equal signs everywhere. So we have 6 times 1/2 times 2 pi would be just pi. 2 times 2 pi for here would be 4 pi. Sine of 4 pi though is, sine of 4 pi would be 0. Okay. Minus 5 root 5 minus 1 over 3. Cosine of 2 pi, well, that would be 1. Minus, what happens if I plug in 0? Well, if I plug in 0 here, that's 0. Plug in 0 here, sine of 0 is 0. If I plug in 0 here, I'm going to get 1. And so if I'm subtracting it, it becomes plus 5 root 5 minus 1 over 3. And you see these end up canceling. And so we just end up with 6 pi. And so the integral of x squared plus y with respect to this area of the region we integrated over is 6 pi. And we didn't do it in rectangular coordinates and leave everything in terms of x, y. We did it in polar coordinates because it just made more sense. This type of figure, which is this donut figure, fits much better into a grid that's made this way than it does in a grid that's made this way. And that's why we made the switch to polar coordinates. And that's why you would think about doing that for a given problem. All right, here's another example. So let R be the region that lies between y is greater than or equal to 0, x squared plus y squared is less than or equal to 1, and then evaluate this function over that region. And we're going to do it using polar. Now, why are we going to do it using polar? Well, it's all because of the region. When we look at this region, first off, the x squared plus y squared is less than or equal to 1. Well, if it was equal to 1, it would be unit circle. And less than or equal to 1 is the entire inside of that unit circle. But y is greater than or equal to 0, so it's really just the top half of that circle. So that's the region we're trying to integrate over. Now, I could do this in rectangular. It's possible. In which case I would say, all right, well, y is measured this way. And y would go between 0 on the bottom, which is here, and this curve on the top. That curve is the circle. In terms of y, it would be y equals the square root of 1 minus x squared. So I could say the square root of 1 minus x squared. X, in order to fill all that space in, goes from here to here. So that would be negative 1 to 1. And so that's one way I could define this region in terms of x and y. If I didn't want to use polar, I could do that. These would be my limits of integration. This would tell me that I have to do y as my variable first for integration. So this is the function I'm integrating. I have to integrate y first, and then I have to use these as my limits, and then x second. Without actually doing that, I think you can see that that will not be the easiest integration to do. But we could set it up. Instead, though, what if I got rid of all this and I said, all right, R is measured this way, and throughout this whole picture, R goes from 0 to 1, no matter where I do this on the circle. So R goes 0 to 1. And theta would make that R rotate all the way through here to fill in this half a circle. So theta would be 0 to pi. Now, in terms of just limits of integration, I think these would definitely be easier. I have all constants. Constants are always easier than functions as my limits of integration. Now, I would have to turn this into a polar function. But I know that dA would be r dr d theta. And as far as dr or d theta, which one we want to do first, it doesn't really matter in terms of the limits of integration, since everything's constant, the orders wouldn't matter. Maybe it would matter when we look at this function. So let's convert the function y times x squared plus y squared cubed. Let's convert that over to polar. Well, y is going to be r sine theta, and x squared plus y squared is r squared, and that's cubed. So ultimately, what do I get? I get r squared, then cubed, they multiply, so this 6th with this extra r, let's say r to the 7th sine theta. So looking at that function, it looks like polar should be a really good bet here. And so if I'm going to do this double integral in polar, I would have this times this. So with that extra r, I get r to the 8th sine theta dr d theta. If I wanted to do r first, sure, r goes from 0 to 1, and then theta second, 0 to pi. But actually, I could split this out completely. Look at what I have. I have a function and a function of single variables multiplied together. And my limits of integration are constants, so let me just do this instead. The integral from 0 to 1 of r to the 8th dr times the integral from 0 to pi of sine theta d theta. That makes it even easier, in which case this becomes r to the 9th over 9 between 0 and 1 times integral sine is negative cosine theta between 0 and pi. Plug everything in, I'm going to get 1/9 times cosine of pi is negative 1, so I would get 1. Cosine of 0 would be 1. Subtract the negative, I get plus. So then I get 2/9, and there's my answer. Now, why did this work out so nicely in polar? Because of this. If I was to grid this off, it grids off much nicer in this fashion than it does if I try and grid it off this way. So fitting it into polar coordinates just makes sense. So to determine whether you want to switch to polar coordinates or not, it mainly has to do with the region that you're integrating over. Does that region fit into a circular system, or does it fit into a rectangular system? And since we're dealing with circles with these examples, polar coordinates make sense. In those past two examples, we were just asked to integrate the function over the region in polar coordinates. Didn't ask you anything about volumes. You didn't have to worry about how the function looked relative to the xy plane, anything like that. In this case, we're trying to find the volume. So we want to find the volume of the solid that lies above the circle in the xy plane. So this is your circle. It's a radius 2 circle. And below the hemisphere, this is a sphere, but the upper hemisphere of a radius 4 sphere. So if I was to draw this, this z function is the upper hemisphere of a radius 4 sphere. How do I know radius 4? Because that's going to be my radius. If I rewrote this, I could say this is z squared equals 16 minus x squared minus y squared. And then I could write this as x squared plus y squared plus z squared equals 16. So it's a sphere, but when we take the square root to get z by itself, we only have the positive square root, so it's the upper hemisphere. All right. That's the function, that's the surface. It's sitting above the circle, and this is a circle radius 2. So now we're talking about the circle radius 2. It's the full circle. That's radius 2. Okay? And we want to do the volume in between. Okay? So this is the volume we're trying to find here. And so it's kind of like a cylinder with this domed top to it from the sphere. And so the way we can do that is simply by doing the double integral over this region. The region is defined by this circle down here of this function 16 minus x squared minus y squared with respect to the area. Now the question is, should we do it in rectangular or should we do it in polar? Well, the thing we're integrating over, if I look at what the region we're integrating over in the xy plane is, it's this circle. It's a circle radius 2. So since it's a circle, I rather grid that circle off this way and create my polar sectors as opposed to gridding it off this way. So I'm going to say let's use polar. So if we're going to use polar, r and theta, r between 0 and 2, theta between 0 and 2 pi, that'll give me the radius 2 circle, and I'm going all the way around the circle, so there's my region. I could rewrite this as 16 minus x squared plus y squared. I'll do that because it'll be easy to convert. And so what I'm going to do is I'm going to have the double integral of the square root of 16 minus r squared, x squared plus y squared is r squared. dA would be r dr d theta, and r is between 0 and 2, and theta is between 0 and 2 pi. Again, it doesn't really matter which variable we integrate with respect to first. Everything here is in terms of r, so let's just get rid of the r's, and then the theta will be real easy. So let's do r's first. We can do it anyway because everything's constant here, but let's do it this way. We're going to use a quick substitution. If u equals 16 minus r squared, du would be minus 2r dr. We have the r dr here, but we don't have the minus 2. So I have this 0 to 2 pi. That's going to sit there. I have a minus 1/2 integral square root of u du. That's what I'm going to have to integrate, and then I'll work with the 0 to 2 for my r. So that's u to the 1/2, so you integrate u to the 1/2. So that would be 3/2, 2/3. I still have this minus 1/2 here, and it'll be u, which is 16 minus r squared, to the 3/2, okay, between 0 and 2. So these 2's will cancel. I get minus 1/3. I plug in the 2, which is 4. 16 minus 4 is 12. So I'm going to get, what, minus 1/2 times 12 to the 3/2. Minus, I plug in 0, I get 16 to the 3/2. I still have the integral from 0 to 2 pi, d theta. All right, I can simplify these. I'm running out of room, so let's start a new slide. I noticed I had a mistake just at the very bottom of that last slide. So it's 0 to 2 pi. This is a 1/3, a minus 1/3, and then 12 to the 3/2 minus 16 to the 3/2. Okay? And I still have the d theta to deal with. Well, all this is one big constant. We could simplify it, but it's one big constant. And with respect to theta, it's that times theta. So I have minus 1/3. 12, I could do the square root of 12. Well, I could simplify that in 2 root 3. And then I have to cube that. So I could say 8 root 3 cubed minus square root of 16 is 4 cubed is 64. And then times theta between 0 and 2 pi. So plug in 2 pi and you get your answer. So I have minus 2 pi thirds times 8 square root of 3 cubed minus 64. And it looks like that answer is negative. It's not, though. Remember, this is the volume. This is the volume what we're looking for. So units cubed, whatever it is. But it looks like this is negative, but it's not, because this is actually negative times this negative. The whole thing is positive. So if you wanted to write it differently, you could say 2 pi thirds times 64 minus 8 square root of 3 cubed. You could do that. It doesn't really matter, but it's not a negative answer. So here's our answer. Good to go. And polar was the easier way to do it. And it's all because of the region that we're integrating over was circular.